Okay, so it's a pleasure to have for this first Crypto Cafe of 2024, Vincenzo Pallozzi Lavorante, who's currently a postdoc at the USF, so almost local, and so he's going to talk to us about some results in coding theory. So we're eager to listen to his talk. Thank you very much, Vincenzo, and you have the floor.
Okay. So thank you for this opportunity. And oh,
We lost you. Are you there?
Okay.
We lost you.
Vincenzo, we cannot hear you. Yeah. Vincenzo, can you hear us? We cannot hear you. Yeah. If you hear us, can you maybe type an answer? Ah. Okay.
thank you. Sorry for the inconvenience. Now, what I'm going to speak today is about locally recoverable codes and the application to distributed storage systems, and also like secret distributed matrix multiplication. Now, this is the main topic that we are going to discuss today. The first one, as I told you, is distributed storage systems and locally recoverable codes. In particular, we will speak about existential results, and we also are going to see how we can apply Galois theory to further investigate other aspects of these topics, like secure distributed matrix multiplication. First thing first, what is a distributed storage system? Now, the purpose of a distributed storage system is to store data. And the idea behind that is that we want to split our information between several servers, and we want our storage system to be reliable. What does it mean? It means that we want to be sure that we can access data even if one or more servers might fail, might collude, or might not be available. And this is why so they are commonly used in application where we need to store a huge amount of data. And as you might already know, so in current era, the storage of information is one of the most important thing for the big companies like Google, Microsoft, Facebook. And as you can see in the following table, many of them, if not all the most important distributed storage system, they use polynomial evaluation codes. And this is why I think that Galois theory is an interesting tool to investigate this area, because Galois theory gives us an idea, a new tool to investigate polynomial, the roots of polynomial, the property, the connection, and it creates a bridge between algebra and field theory. So, as you can see, we have Reed-Solomon codes, and Reed-Solomon codes as locality, which equals the dimension. So that might be good sometimes, but sometimes that might not be good. In fact, as you see here, we have dimension of the code, which equals the locality. And the reason why that happens for every of those code is because classical Reed-Solomon code for this purpose, they can only recover at most d-1 erasures by looking at the dimension of the code. But let's try to understand a little bit better what we are trying to do. So two main properties that we want from a reliable distributed storage system, they are the repair degree and the repair bandwidth. And in particular, the repair degree is the number of nodes that we need to access if we want to recover lost information, while the repair bandwidth is the amount of data that we need in case we have a node failure. In this presentation, we focus on locally recoverable codes. This means that we focus on the repair degree. And in fact, we will see how those are one of the best way to minimize the repair degree. What is a linear code? Well, a linear code C as a subspace of Fq to the n, where Fq is the finite field of Q elements. If the dimension of the subspace is K, and if the minimum distance between the code words is D, then we say that C is an NKD code over FQ. In particular, in this case, with code, we mean linear code. So we are only interested from now on in linear code. Now, this is a nice overview of the meaning of the parameters, where n is the length of the word. Of course, k is related to the number of words we can use in our code. And d usually is one of the most important parameters because it allows us to know how many errors we can detect. Okay, now, what is a locally recoverable code then? A locally recoverable code basically is a linear code with the additional property of locality. But we say that a linear code C has locality B if we can recover any deleted component of a code word V in C by looking at most other B components of the code word V. Now, we will write that C is an NKDB locally recoverable code. Again, we can use for this purpose a nice picture of the situation. So we can see, we can use sets and points to represent what is a code word and what is the connection between its entries. In this case, what we can see, we can imagine our code word to be a set, for example, and if we have like 5 dots, this means that the code word has 5 entries, and the locality means that each point in a set can be recovered by looking at the other elements. This is a nice way to represent what is the meaning of locality. So we want to be able to recover one lost information by looking at most other B given neighbors. Okay, in the picture, we have that B equals 4. So any of the 1 dots that we might lose can be recovered by looking at the other 4 elements. And again, I'd like to point out that in this situation, we are not doing error decoding, but we are doing erasure decoding, which is different because if you remember, I told before that usually a code can detect d-1 at most d-1 over 2 errors. But in this case, since we are not interested in a transmission of information, but we are just interested in a storage of information, we have an additional property that we know where is the missing element. And when we want just to retrieve an information that we know where it is, but we just cannot access, then we will speak about erasure repairing, okay? And in this case, any linear code with dimension k can recover at most d-1 erasure by looking at k other elements. So basically, any given code has the property to be locally recoverable in a certain way. But the point is, do we really want to look at all k values anytime we need to recover just one erasure? Sometimes that might not be the most efficient thing we want to do, because sometimes it's very likely that we only have one erasures, and we would like to say, okay, if I only have one erasure, I don't need k elements. Maybe I need k elements when I have d-1 erasure. Okay, that's fine. But if I only have one erasure, is there any way I can recover it accessing less symbols, using less energy? So that's another picture of the situation. And this is an example where we have a locally recoverable code. In fact, in the situation, a code word of length 10 is divided into 2 subsets, which means that if I take an element here, I don't need all k elements of the code word, but I can just look at 1, 2, 3, 4 elements inside this set to recover this lost symbol. And the same thing happens here. So from now on, remember, when I speak about locality set, I mean this representation here. In this case, we have 2 locality sets, and we have locality b equal 4. Now, what's next? So locally recoverable codes have been intensively studied in the recent years, and sometimes they might require 2 additional properties. Those 2 properties are the goal, basically, of the purpose of this presentation, because my aim is to show that using Galois theory, sometimes we have the tool to extend the state-of-the-art constructions and give them additional properties. Now, hierarchy is what we want when we want to correct multiple erasures, because of course, might be interesting to correct 1 erasure, but what happens if I have 2, 3, 4 erasures? Can we still recover the lost information? That's hierarchy. The second property is availability. Now, availability is clearly understood because of the name, and we just want to have multiple recovery sets. So again, what happens if I cannot access one locality set, one recovery set, which is a synonym of locality set? Then we might need to have multiple ways to recover one lost information. And before going deeper into that, we just define what is the meaning of locality for multiple erasures. And the locality for multiple erasures, we just need to be a little bit more precise when we define it. So we say that a code C can tolerate X erasures on a set S of indexes if whenever we have X erasure on the set S, we can recover those erasures by looking at the other elements of the set. So basically, we have a set of indexes. We have a number of erasures inside those set of indexes. We want to be able to recover X erasures by looking at the other elements coordinates in S. Okay, so it's just a generalization of what is the one locality. Instead, now we have X erasures instead of just one. And this allows us to define what we will see later, some construction of what is known to be hierarchical locally recoverable code. So basically, we don't only have those 4 parameters, but we had 2 other parameters. So we have A and we have lambda. Okay, and basically what happens here that while we need B elements to recover one erasure, now we ask that we also have another property, which is that we can recover lambda erasures by looking at most a other element. So that's the meaning of the definition. And this is the formal way we can define. And I'd rather show you this picture because it's quite intuitive. Well, what is our idea of implementing hierarchy? And we will see a little bit better later why we have this structure. But what I'm interested in now is show you how it works, what it means to have like a hierarchy. In this situation, if I want to recover this lost symbol, I can either look at 2 symbols here because they are inside the same locality set, or I can look at those 2 symbols and those other 3 if I want to correct multiple erasures. So for example, if I don't have those 2, I can look at 1, 2, 3, 4 and recover 2 erasures instead of just 1. So that's the idea behind hierarchy inside a locally recoverable code. So the smaller set gives you the one locality, while the bigger set can tolerate lambda erasure. In this case, lambda is equals 2, but it can tolerate more than 1 erasure. And this is instead the definition of availability with a picture below. And basically, availability means that we want to find a way to partition the entries of our code word, that in this case are the dots, in such a way that each of them has 2 locality sets where it belongs. So that even if we cannot access one locality set, we can use the other one and still be able to recover the element that is missing. In this case, the idea is to use orthogonal partitions, and the idea was used in one of the most important construction, which is due to Thamo-Varga, and we will see better in a few moments. Now, like in any situation where there are some trade-off involved, we want to know what is the best possible set of parameters that we can have when we construct locally recoverable codes. And there are generalization of the famous singleton bound. Well, for people that...
Yeah,
Sorry?
these ladies, they have to work with him. They say that many people.
Okay. So in the literature, there is the singleton bound, which gives you the best possible trade-off for a linear code, right? Now, there are generalization to the locally recoverable codes that I put here. And this is just, we cannot have parameters that are too much better. They still need to satisfy this equality. And anytime the quality is attained, then we speak about optimal locally recoverable codes, okay? Now, if we have hierarchical locally recoverable codes, the state of the art was telling us in 2015 that the best trade-off possible was this bound, and if codes that attain this bound, they are called optimal hierarchical locally recoverable codes. Our contribution for what is the aspect of optimality was to prove, using, of course, Galois theory, that when lambda is lower or equal than b, which means that when the number of the region that we can correct is still inside the smaller locality set, then we have a better bound. We prove a better bound for hierarchical locally recoverable codes, and we were able to show by comparison that our new bound was better than the previous one for an infinite set of parameters. So that's a very interesting thing. But what is even more interesting is, can we find a family of codes such that they attain the new given bound? Because of course it's interesting to prove an arithmetic bound, but if we are not able to show codes that attain that bound, that's a little bit incomplete. Okay, so now let's go on with optimality. Singleton bound for locally recoverable codes with availability. Again, I don't want to waste too much time here. It's just another other two bounds that can be attained. Now, let's start looking at the construction. If we want the best of the best when Q approaches N, which means when the cardinality of the field is close to the length of the code, well, the best of the best for locally recoverable codes, it's likely to be the Thamo-Bar codes given in 2014. Okay, they were able to provide an optimal family of LRCs, and now they also suggested a way to implement hierarchy and availability by using their construction. But while the main construction of LRCs is probably the best known, the generalization that they provided, they have some arithmetic restrictions. They are not, the construction for hierarchy and availability is not very flexible. So one goal that we had was we want to find a way to generalize the Thamo-Bar construction, which is the best thing that we see in the literature, and giving availability and optimality, but still without the restriction that they suggested. And also, we want to be able to correct multiple erasures, maintaining the optimality. And again, why Galois theory here? So Galois theory, it's important because it provides a better understanding of what was the main tool that they used in their construction. Because in their construction, they introduced the idea of good polynomial, okay? And the reason why Galois theory helps us here is because it can relate the property of being a good polynomial to the property of the splitting field of the polynomials. Okay, so one way to investigate a new property is try to understand what it relates to and use deep mathematical tool to investigate even better. Now, what is a good polynomial? The definition says that a polynomial is RL good if the degree is R plus 1 and if there are L distinct subset where it is constant. Okay, each subset needs to be of the maximum cardinality possible for the polynomial to be constant. In fact, we want that the cardinality equals the degree of the polynomial. So that's a very easy definition. But what is important is that this property relates to the property of a polynomial to split completely. Now, we say that a polynomial f splits f in fqx minus t naught splits completely if we have that it splits into degree of f distinct factors. And the reason why it is connected to the previous definition is that anytime we have a point t naught for which f of x minus t naught splits completely, then the set of roots is a set where f is constant. So as you can see, finding a set where f is constant, it looks like it is equivalent to find a certain point t naught for which f of x splits completely. So that's the reason why Galois theory is important, because Galois theory provides numerous tools to investigate the splitting properties of a polynomial. We will see that before the end of this presentation. Now, our goal is to use this understanding to generalize the Thamo-Bar construction. And what was our idea? We thought that what happened if instead of using just one polynomial and use just the valuation of one polynomial, so just the splitting field of one polynomial, we use nested polynomials. What happens if we study what is the splitting property of the composition, for example, of f and h? So the main tool was that we were able to prove that if we require this polynomial to be completely split for some element, then we also have that the polynomial h, which is inside, it also has the nice property to have a totally split place, which means to have a set bi where it is constant, okay, where bi is of degree of h. So basically, we were able to create a nice structure where we have a bigger set and a smaller set inside, where the polynomial f of h was constant on the bigger set, while the polynomial h of x was constant on the smaller set. So that's why we call nest and subnests. Okay, so a nest is the bigger set for which f of h is constant on. And furthermore, we know that by using the previous proposition that in this situation, there are also subnests where h is constant on, okay? So that's basically the main tool, the main setting that enable us to provide a new construction of hierarchical locally recoverable codes. And we will say that two such polynomials, when they exist, they are called L-nested if they have the property that f of h minus t naught splits completely over fq for at least L elements t naught. So this is the situation, again, a little bit more precise here with some names. Now, we have, in this case, two subnests and one bigger nest. And of course, we want to have that cardinality of each set equals the degree either of this inner polynomial, so 3 needs to be equal to 3, and the bigger set needs to have the same cardinality of the composition of the two polynomial, which means 6 needs to be equals to 3 times 2, which is 6. This is our main result, because by using this construction, not only we were able to construct a new family of hierarchical locally recoverable code that was optimal for the previous bound, but those codes are actually optimal for the new bound that we found and we discussed before. And that was the main ingredient. So we have still evaluation polynomial evaluation codes, and the nesting property can be seen here. So basically, we are evaluating polynomials that are nested, and we work on the degree of the sums in order to have the locality. In fact, now we won't look at every detail of the proof, but just to give you a sketch of why our code defined in this way, they have locality, is the reason. Because if we take the polynomial m, so all this big guy here, and we restrict the evaluation on the smaller set, what happens is that this polynomial, it is constant, okay? As you can see, we have f of h and h, they both are constant of the smaller set, because that's exactly the purpose of our construction. The smaller set is a locality set for both f of h and h, which means that using a Lagrange interpolation, so a Stardom technique of interpolation, we can recover one lost symbol by looking at the other, because the degree of the restriction is exactly b minus 1, but we are left with b symbols, so we can recover the polynomial. And for the bigger set, the idea is pretty much the same. The only difference is that in the bigger set, only f of h is constant, because the bigger set is a locality set only for the composition, which means that the restriction now has degree, which is this guy here, which equals to a minus 1. Again, standard Lagrange interpolation allows us to recover the lost symbol by looking at the other a symbols. And that's basically the idea to give a locality to our construction. This is a toy example, and just to show you how to picture the image, this is an example of a polynomial that we are going to evaluate, and this is the structure of the point. So we know that evaluation of this is either 1 or minus 1 by using h, and when we evaluate with f of h, then it's just constant for every point of the set. Okay, so you can just see that those 3 points, they have same evaluation here, and that's representing the evaluation of with h, and then it becomes the same one when we evaluate by using also f. Okay, now what about availability? Again, for availability, we needed to find a way to give more than one locality set. And we found like a new interesting way to do that. And what we did was, what happened if instead of asking for a polynomial to be constant on a locality set, we allowed to the polynomial to be linear on the locality set. So basically, what happened if we allow the polynomial to be linear so that it might get into multiple, it might exist different polynomial such that we have this equality satisfied. And what happened is that we are looking for those kind of collisions. So we would like for a given f to have two different values, a and b, and a prime and b prime, for which they collide. And what is interesting is kind of similar to what happens for the birthday paradox, is that those collisions, they actually appear to be frequent when we assume random distribution among the zeros of the family of the polynomials. So basically, we were able to construct a new family of optimal locally recoverable codes with availability by studying those properties, by proving that that situation actually happens. And not only that, but we were able to prove that our family of code with a viability, they are optimal, not only with respect to the generalized locally recoverable code with a viability singleton bound, but also for the classical standard singleton bound for locally recoverable codes, which is a quite surprising result, because basically we add one property, which is the viability, while we still attain the bound for locally recoverable codes that they usually don't have a viability. And this is a kind of interesting result that might lead to further investigation of what is the reason behind that. Is maybe that the classical locally recoverable codes, singleton bound, might be generalized under certain parameters. That's still an interesting question to know. And this is just an insight to the approach. So when we allow polynomials to be linear, this means that they can have at most one intersection with another polynomial, which is linear on a locality set, and that's the situation that's happening. So each code word, each entries of a code word belongs to numerous locality set, and that's happened for any of those. Okay, so that's the idea. We just try to extend what is a good polynomial to for having multiple recovery sets. Okay, now we will be a little bit faster here because we start a little bit later. So I just wanted to show you that actually Galois theory play a huge role here, because everything we said makes no sense if we are not able to prove existential results. So basically, if we're not able to prove the existence of nested polynomials, if we are not able to prove the existence of paradoxical sets, if we're not able to prove existence of what we define, that our work would be without interest. But the thing is, we can actually use Galois theory because estimate the number of T nodes such that F minus T naught splits completely can be proven to be equal to estimate the number of totally split places of a given extension. So now, when we use the terminology of extensions, Galois extension, Galois closure, we can use numerous results deriving from Galois theory. And that's the main theorem that allows to connect what happens with the totally split place of a given polynomial and how can we estimate the number of totally split places by using some ramification theory where M of F is the Galois closure. And basically that's what we were able to prove. We were able to prove to estimate that there are in fact at least this number of totally split places. So we have, by working with the cardinality of the field, we are able to always provide the family of polynomials that we need to construct our hierarchical locally recoverable codes, and also with a viability. Okay, and that's a sketch of the proof. We can skip this. That's just interesting that we use this property, which is connected to the theorem I showed you before. Now, just a quick view into the second topic, which is secure distributed matrix multiplication. The key point of secure distributed matrix multiplication is that we want to distribute it, a heavy operation, into n workers. So instead of storing information, what we want is that a user needs to usually compute an heavy computation, which most of times is the multiplication of two matrices, and we want to be able to use servers to ease the process, but we also want to be secure that what we give to the servers is secret. So even if X server colludes, their shared information is not available. This is a picture of what happened. A user gives information to the server in order to compute a matrix multiplication, even if one server doesn't work, or one server is an adversary server which might want to take information that need to be considered, and it's to be still working the whole procedure, and the worker tree we don't want him to be able to recover any information, any secret information that the user is sharing. Now, recently, many constructions have been presented. The one we focus on today is the secure math construction. And the main idea is that they use Reed-Solomon codes in order to build a secure distributed matrix multiplication. And the reason why it works is because basically the dual code of a Reed-Solomon code defined over FQ contains all the polynomial of a given complementary degree. So basically, it's possible to recover information by using an equation given by the dual code. And of course, if we have an equation, let's say, which A, B plus CD equals 0, we can recover AB by knowing CD, of course. And we still don't provide any information about AB. Now, the reason that's just explanation of how it works. Basically, we have two matrices. We partition the matrix in a way that the product is just the sum of the pair-based product AI, A1, B1 plus ... AP, BP. So that's the reason why we want something which is connected to the orthogonal, to the scalar product. And the security is added by inserting a certain randomness here. So instead of using a code of dimension P, which would make sense since we just want to send P information, if we want security, we need to add X symbols, X random symbols, in order to provide security of our protocol. And that's the reason why the dimension here is P plus X. And that's basically what they do. They encode the information using polynomials. So f of A is a piece of the matrix, G of A is a piece of the other matrix, such that when we do H A times B, that is just the sum of H of AI, where H is the product of those two polynomials. Now, we just upload the information regarding the server that we don't care. So this random part, we just upload the random part. Remember, P indexed the part which needs to be secure. We just upload what is not needed to be secure. But since we have control on the degree of the polynomial, then we can find a polynomial of a given degree such that satisfies this equation because it is in the dual code of the Reed-Solomon code induced by little h. Now, if we have this equation and we can have h to be constant on the set that we want, then we can retrieve the first P symbols. And basically, that's what they do. Now, the problem is that there are some restrictions. For example, they need the entire field because they need the property of the code to be the all Reed-Solomon code if we want to have in the dual any polynomial of a given degree. So what if we can't use all the field? What if we need to use certain restrictions? So the goal was to build a generalization and extension of the previous math schemes for an arbitrary length lower than Q. So, and the idea that our contribution was to use generalized with Solomon code and controlling the dual by using a suitable linear equivalence of codes. So this is the main ingredient for our contribution, was to say, oh, look at that. We can describe what happening with the product of the two polynomial by using the star product of the code. So the star product is just the code obtained by doing component by component multiplication of the code words. Okay. And the main idea was that if we look at the Magda schemes in terms of the star product of codes, we realized that the key property that they need to satisfy is that in the dual of the star code, we need to have a code word with all constant entries in the first P entries, because they are the entries we want to recover. And why, if we have this code word, then we are okay? Well, the reason is that, let's say we have this situation where we want to retrieve the product AI BI plus dots AP BP, which is A times B. Now, in the star code, these two code words becomes this one. Now, if we have these code words here inside the dual of the star code, and let's call this code word C star, then this follows. We can retrieve the first P information by dividing for lambda. In fact, if we multiply by lambda here, then what happens is that we have the first lambda entries. So it's exactly the equation given by the dual code. And so how can we approach this task? We can use generalized Reed-Solomon codes because we have more flexibility on the parameters and more control on the evaluation. And also, however, we need the code equivalence because we don't want just any lambda to be here. Because basically, if we don't have that, we need to use linear code equivalence in order to have lambda here. But since we want the two first code to be equivalent to the code, to the star product of code we obtain, we need a quadratic element here. Because if we have a quadratic element here, we can transfer one lambda for C1, one lambda, let's say this is lambda square, okay? We can transfer lambda here, and so we have two equivalent code to the one we had at the beginning. So basically, this is just to give you an insight. Of course, I don't want to be give you all the details. I can't give you all the details, but we still need to use code. We still needed to use code equivalence and choose suitable polynomials for quadratic transformation. And thank you for today's presentation. That's all. I'm sorry if I had to rush a little bit on the end due to the time. So if you have any question, I'm happy to answer.
Thank you very much, Vincenzo, for the very interesting talk. Yeah. I see there is a question in the chat, which I can read to you from Yannis. He says, what is the criterion for characterizing a node as good actor or bad malevolent actor?
So basically, that's usually relevant here. So we just say that a node here. So we distinguish the node into three categories. One is a good worker, which is just a worker who works as it should be. So it does not leak any information, and it does actually work. So we can use it. Then we have what it could be bad, like a bad worker, which is just some node that does not work. Okay. So basically malfunctioning. So you cannot access the information, you cannot access the server anymore. And the third one is the adversary, which is just a node which works, but it might be used from an adversary to extract information about the information you send. So for example, here, if you send us A3B3 tilde, then the malevolent actor can access A3 tilde, B3 tilde, and try to get information about the original matrices that you are using. So that's like the definition.
And you are monitoring these requests and you classify
No,
as an
no.
attack.
So the fact is, you want to build a secure distributed matrix multiplication that allows you to be protected from any of those situations, even if you don't monitor. So the point is, for example, the secure math dot, they are, we can say that they are X secure, which means that for if at most X worker collude, we are still okay. We still don't leak any information, okay? So we don't need to monitor. We know that if we are guaranteed that we have at most X number of colluding server, we are okay.
Thank you.
Any other question from the audience? I have maybe a question regarding when you were mentioning the last result on in the first part of the talk about split places. Are you using some kind of Chebotarev density argument?
Yeah. Exactly. So basically, the Chebotarev density argument, it used in the proof of this result here. Okay, so it allows us to estimate the number of totally split places by using the cardinality of the Galois group of F and ramification of the Galois closure. So the reason why it helps us is because we don't actually need to calculate the totally split places of F, which might not be of Galois closure, but we can use actually a Galois closure and then the group of F, which can be estimate given it has at least one totally split place, which is always basically most times the case. So that's all the theorem.
Great, thanks.
And our generalization in this case was to study what happened if we have f of h and what happened to the composition by knowing what is the situation for just one polynomial. So basically, we had to generalize the construction and the theory. So the construction was taken from Tamobarg, and the theory was taken from the result due to Micheli.
Thanks. Any question? Okay, so I think we can thank our speaker again. So thank you.
Thank you.
Thank you, Vincenzo, and so see you in 2 weeks. Okay.